talking about theoretical and experimental probability. So there's two different types of probability we're looking at today. Theoretical is what could happen in theory. If all outcomes are equally likely, the theoretical probability of event E, so this means probability of E, is the number of favorable outcomes to the total number of outcomes. Let's look at an example. So I'm not going to actually perform an experiment. I'm not going to actually spin this spinner and see what happens. I'm going to talk about, in theory, what could happen. So if you spun it once, write each probability as a fraction, a decimal. Well, fractions always in simplest terms, a decimal and a percent. So first of all, how many numbers? There's 16 possible outcomes on here. How many are a multiple of 3? What is the theoretical probability, of spinning a multiple of 3? So 3, 6, 9, 12, 15. 1, 2, 3, 4, 5. So 5 of these out of the 16 total could theoretically be a multiple of, could be a multiple of 3. So in theory, I have a 5 out of 16 chance. And if you divide that and turn it into a decimal, you get 0.3125, which is also multiplied by 100, and you get the percentage, 31.25%. So what is the, let's skip the next one. We're going to look at the one that says or. Probability of an even number or greater than 5. Remember that or is kind of like all, those are both possibilities. It's not and, so it doesn't mean they have to both be true. Even number or greater than 5. Well, let's look at the greater than 5 first. What's greater than 5? 6 through 16. Which other ones are even? 2 and 4? So that's basically everything but 1, 3, and 5. So that's 13 out of 16, which if you turned that into a decimal, you're going to get 0.8125, which is 81.25%. And then we have the and. What's the probability that it's odd and at most 9? Wouldn't that be less than or equal to 9? Yes, so what do we have? We have at, this has and, that means both conditions have to be true. At most 9, so the biggest it can be is 9, so we're looking at these numbers, and odd, 1, 3, 5, 7, 9. So there's 5, so it's actually going to be the exact same answer as A, 5/16, which is 0.3125, which is 31.25%. All right, let's look at some others. We're still doing theoretical probability. We've got a pencil box with 5 red, 12 blue, 10 green, and 3 yellow. I usually just count the total first because that's going to be your denominator. Okay, which if you count those, you get 30. Now, what are they asking me for? Probability that it is not yellow. So I want how many are not yellow. Wouldn't it be easier to count the ones that are yellow, 3, and substitute from the total? And now I get 27 over 30. My directions say simplest terms, divide both by 3. And theoretically, I have a 9 out of 10 chance of spinning of reaching in the box and getting a not yellow. We're going to skip this one. I'm going to go on to this one. So, just to make the notes shorter. 2 standard dice are rolled. So that means 6-sided. What's the probability that the sum of the 2 dots is at most 5? So that'd be less than or equal to 5. I need to look at my sample set. This isn't an easy one to say I've got this many options. Okay, I could get a 1 on the first die, a 1 on the second. 1 on the first, 2 on the second, 1 on the first, 3, 1, and 4. Now, if I did 1 with anything else, I'd get more than 5. So I got to stop there. So what if the first die was a 2 and the second die was a 1? What if I had 2 2s? And a 2 and a 3, that would work. I'm done with the first one being a 2. Let's see, what if the first one was a 3? I could have a 1, a 2, that's it. If the first one was a 4, I could have a 1. So those are all my choices of what combinations of 2 die could get me a sum of 5 or less. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, whoops, I put it on the bottom. 10 out of, how many total are there? 6 choices on the first die, 6 choices on the second die, 36. Remember, this is from counting outcomes yesterday. And then we divide both of them by 2, and we get 5/18. Now we're going to turn the page, and we're going to look at theoretical probability with a Venn diagram. So these students that are in the box are all in the same homeroom. They were asked if they have a part-time job. So here's the part-time job circle. And if they have a driver's license. So here's the driver's license circle. Then we're going to look at theoretical probability if you chose a student at random. So what's in simplest forms? What's the probability that a student has a part-time job? Well, you have to look at the pink circle. How many are in the pink circle? 14. How many total students are there? If you count all these students, you're going to get 25. That does not reduce. All right. How many have no driver's license? Well, these are the ones in the driver's license circle. You could subtract them from 25 and get 12. Or you could add the 8 and the 4 because they're not in the driver's license circle. You still get 12. Okay, which kids have both part-time job and driver's license? That's the 6 that are in the center where it overlaps. We'll skip down to the last one. Which kids have a driver's license but no part-time job? Here's the driver's license circle, but these also have a part-time job. So I'm going to put 7. All right, one more vocabulary term, I guess. Complement of an event. The complement of an event is the probability of the event not occurring. The sum of the possibilities is 1, which can be converted to 100%. Therefore, the probability of it not occurring, that's what this little curly Q means, is the probability of not E is 1 minus the probability of E. So whatever the probability is, you take it away from the total and you get the not probability. So if the probability it will rain tomorrow is 11/15, what's the probability it will not rain? You just go 15 minus 11 4/15. All right, experimental probability is our other kind of probability. This is when you actually perform the experiment. So it's based on results of repeated trials. So instead of looking at what could happen, what the theoretical probability is, I'm going to look at what did happen when I spun it. But I'm going to look at both. I'm going to compare. So what is the theoretical probability of spinning an orange? That means I don't look at the trials. I don't look at what actually happened. I look at the spinner. How many are orange? 1. How many total? 5. So theoretically, I have a 1 out of 5 chance of spinning orange. But on my experiment, what actually happened? I actually landed on it 12 times out of 50. It was spun 50 times. When you reduce that, you get 6/25. Now, if you're comparing, this would be 5/25, so it actually happened a little more, but very close to the theoretical probability. So what's the probability of red or green? Okay. Over here, if I ignore the experiment, in theory, red and green make 2 of the 5. But if I look over here, what actually happened in my trial, red and green make 15. So it actually happened 15 out of 50, which reduces to 3 out of 10. This would be 4 out of 10. So it actually happened a little less than the theoretical, but very, very close. All right, what's the probability of not purple? Well, purple's only one of these. So 4 out of 5 chance of getting not purple. And then how many times did it actually happen? Instead of counting those, I would say 50 minus 7, 43 50ths. That does not reduce. Now this is like 40 50ths, so it happened a little more than the theoretical. If you wanted to compare these and you were struggling to do to convert them to comparable fractions, you could always convert them to, divide them, convert them to a decimal or percent and compare them that way. But that's theoretical and experimental probability.